All right, separation of variables. So today we're going to talk about how to solve slightly more complicated differential equations. So up to this point, we have solved fairly simple ones, differential equations, say of this form, where my derivative is only some function of x, like x squared. And then the way we can solve that is by finding the antiderivative of the derivative, x cubed over 3 plus c. But if you take a look at these differential equations we have down here, I don't have a derivative that's only a function of x. It's a function of x and y. Here, it's a function of y, and here, it's a function of x and y. So we're going to talk today about how we can solve differential equations of that form. Now, these differential equations are what we call separable differential equations. And a separable differential equation is any differential equation that can be written in the form of derivative is equal to something that is only a function of x multiplied by some other thing that is only a function of y. So it has to be able to be written that way, as a product of something that's only in terms of x and something else that's only in terms of y. And then we'll go through the process on how we can solve that. Just remember, the solution to a differential equation is a function in the form y equals some f of x. Perhaps I shouldn't use f here because I'm using f up there. Y equals some h of x. In other words, that y is equal to a function of x. All right, so let me go through this process here. So first thing, we're going to solve this differential equation here. Remember, what we're looking for when we solve a differential equation is we are looking for a function that when you take its derivative, it satisfies that equation. So we need a function here whose derivative is equivalent to 3x squared divided by e to the 2 times that function. So first step is to verify that this is in fact a separable differential equation. Note that I can express this as 3x squared times 1 over e to the 2y. This first term is only a function of x, and it is being multiplied by a second term that is only a function of y. So it satisfies what you see right up here. So that's how I know it's separable. Now, the way that you solve a separable differential equation is you separate the variables. So what I'm going to do here is I'm going to endeavor to get all the x's on one side and all the y's on the other side. So I'm going to start by multiplying both sides of this by e to the 2y. That will allow me to get rid of the y's on the right-hand side. And then I'm further going to also multiply both sides of this equation by dx. That's going to allow me to get rid of the x's on the left. And now, if you see what I have here, I have e to the 2y dy on the left and 3x squared dx on the right. So I've now separated the variables. I'm now going to integrate both sides. So we're going to do an antiderivative on both sides of this equation. So bring it over here. The left-hand side has an antiderivative of e to the 2y divided by 2 plus some c. You could do a u substitution on this, letting u equal 2y, and then du will be 2 dy, and that's how I got that. Or you can just recognize that because the derivative of the inside is a constant, because of the chain rule, when I would take that derivative, I would multiply by that constant. I'm doing an antiderivative, so I can just divide by the constant. And then on the right-hand side with the x's, the antiderivative of 3x squared is x cubed plus some other c. Now, I can't have plus c on both sides because that is implying that it's the same c, and I really have no idea. So let's call the c on the left C1 and the c on the right C2. They're different. But if I just subtract C1 on both sides, I'm going to end up with e to the 2y over 2 is equal to x cubed plus. Now, C2 minus C1 is some unknown constant minus some other unknown constant. Let's just call that C for an unknown constant. So in the future, I will not be writing a plus C on each side because, as you can see, if you write plus C on the left and plus C on the right, you can just turn that into a single plus C. So we'll just do that from now on. All right. Now, we need to do two things here. Ultimately, we need to solve this equation for y. But because this is an initial value problem, and by initial value problem, I mean we have been given a way to find c, I'm going to go ahead and do that right now. So I'm going to go ahead and find the value of c right now. And I'm going to do that by plugging in 0 for x and 1/2 for y, and then solving for c. So if I plug in 0 for x and 1/2 for y, I will get this. So that's going to tell me that e over 2 is equal to c. In other words, c is e over 2. So now that I've determined the value of c, I can substitute that value of c back into this equation right here. And what I will now have is e to the 2y over 2 is equal to x cubed plus e over 2. All right, so now I can solve the equation for y. And in order to solve for y, I need to get to this y right here. So first step is multiply everything by 2. Next, to get the y out of the exponent, I'm going to take the natural log on both sides. When you take the natural log of a sum, there's no rules for logs to separate that. So it just becomes ln of the entire side, 2x cubed plus e. What does this turn into? Well, the natural log and the e are inverses. They undo each other. So I'll have 2y on the left, ln of 2x cubed plus e on the right. And then the last step is to divide both sides by 2. So y is half of the natural log of 2x cubed plus e. That is the particular solution to this differential equation. There we go. All right, so what did we do there? Just a review. I started off by separating the variables. Multiply or divide to get all the x's to the right-hand side and all the y's to the left-hand side. You'll see that that's right there. Bullet point number 1. Get all the y's on one side and all the x's on the other. Step 2, integrate both sides. So that's what I did right there. Step 3 is to use the initial condition, if given, to determine the value of c. So that's what we did right here. And then your last step is to solve for y. Now, in some cases, you will not be given the information to find the value of c. If you're not given this initial condition, if you're not given this input right here, then you won't be able to find c. And in that case, you will just leave c in the equation and you will solve for y, and your y will end up having a c in it. So if you look over here to my equation there where I have that e, I would end up having an unknown constant c in that position because I would not have known what was there. All right, let's go on and do another one. We have a derivative dy dx is equal to 2y squared, and they've given me an initial condition, y is equal to 1 or negative 1 when x is equal to 1. And this time the question is going to be what is x, or when x equals 2, what does y equal? So what I'm going to do here is I'm going to go through and do as we did before, solve for the equation that satisfies the differential equation, and then we can plug 2 in to get the answer. Now, first question is this a separable differential equation? And it is, because we can express it as 1 times 2y squared. And we can consider 1 to be the function of x and 2y squared to be the function of y. So this is separable. So what I'm going to do is I am going to separate. So I'm going to divide. So the 2y squared, the 2, I could divide the 2 over with the y squared, but generally I'm going to choose not to do that. I'm going to leave the constant 2 over there. In fact, maybe when I expressed it, what I should have written is I should have said, all right, the 2 is the function of x, and the y squared is the function of y. It doesn't really matter. The constant can be on either side. So I'm going to leave the 2 on the right-hand side. I'm going to divide both sides by y squared, multiply both sides by dx. Remember that it's only through multiplication and division that I can do separation. No adding or subtracting. All right, so integrate both sides. Antiderivative on the left-hand side is negative 1 over y using the power rule. Antiderivative on the right-hand side is 2x. And as I discussed up above, we're going to then tack that plus c on only to the side with x. All right. Next step, solve for c. So I'm going to substitute in negative 1 for y, positive 1 for x, and I'm going to determine that c must be equal to negative 1. Substitute that back in up here, and that will lead me to negative 1 over y is equal to 2x minus 1. And then I'm going to solve this for y. So I'm going to take the reciprocal on both sides. Actually, let's take the negative on both sides, the opposite on both sides first. So I took the opposite on both sides. And now I can just take the reciprocal on both sides. So there I go. Now, if I was just trying to solve for the function, I would be done. But this one is specifically saying when x is equal to 2, what does y equal? Well, now I can just plug 2 in for x, 1 over 1 minus 4, or negative 1/3. All right. Last one here, find the equation of the curve that passes through the given point. So that's my initial condition. I'll be using that to find c. And it has slope given by. So slope given by means they're giving me the derivative, y over x squared. All right, so separate. So in this case, I'm going to separate by dividing both sides by y, or multiplying by 1 over y, and multiplying both sides by dx. So dividing by y gets rid of that y right there. Multiplying by dx gets rid of this dx here. Result 1 over y dy is equal to 1 over x squared dx. Integrate both sides. Now here's where you have to remember that this is a special case. 1 over y has an antiderivative of ln absolute value y. Antiderivative of 1 over x squared, negative 1 over x plus c. I'm going to go ahead and solve for my c now using 1 for x and 3 for y. So ln 3 is equal to negative 1 plus c. Therefore, c is the natural log of 3 plus 1. All right, take that c value, put it right here, and go ahead and solve that for y. So ln absolute value y is equal to negative 1 over x plus c, which is ln 3 plus 1. Now I need to solve that for y. We always have to solve it for y, get it in the form y equals. So to get rid of the natural log, I need to exponentiate both sides. So I'm going to raise e to the power of both sides. I'm going to have the absolute value of y because the e and the ln are going to cancel out. Now, when you raise e, I could just leave it the way it is on the right-hand side. But with exponentials, there's a way you can simplify it. I can rewrite that right-hand side as e to the 1 over x plus 1 times e to the ln 3. Now, all that I've done there is I've kept the negative 1 over x and the 1 in the exponent, but then that ln 3, instead of leaving it in there, which I could have, I've decided to write it this way instead. And so what I'm using, let's go off to the side here, is this idea that e to the x times e to the y is equivalent to e to the x plus y. Therefore, if you have a sum inside an exponential function, you can write it as the product of e raised to each term. And so that's what I've done here. I've only chosen to pull the ln 3 out. And the reason I've done that is because e and ln can now cancel each other out, and I can express this as absolute value of y. This term right here is just going to become 3. You don't have to do that, but it just looks nicer that way when you can pull that 3 down in front. All right, now I need to get rid of this absolute value on my y because I need to solve this for y. And so just if you think about what does it mean if I tell you that the absolute value of x is equal to 4? Well, it means that x is either plus or minus 4. So what that means is you can drop the absolute value by simply applying a plus or minus to the other side. So going back over here, I can drop the absolute value by applying a plus or minus to the other side, like so. Now, I need my y to be a function of x. Plus or minus is not a function because you get two different values for any one input. So whenever you have an absolute value or maybe a square root and you end up with a plus or minus in your y equals equation, you have to go back to the initial condition to figure out which one it is. So remember that when we plug 1 in for x, we need to get 3 for y. So if I plug 1 in for x, I need to get 3 for y. So I have 3 is equal to plus or minus 3. I need to choose the plus, not the minus. So what that tells me is that my final answer is 3e to the negative 1 over x plus 1.